Welcome to the last lesson of this unit, working with formulas. Our goal today is that you can eventually evaluate formulas by substitution, and apparently I've got a typo here, by substituting values for the variables. And you can rearrange formulas for one of the variables. You can determine the type of function a formula represents when some of the variables are replaced with values. And that will make more sense as we go through this. But feel free to correct my typo there. That was supposed to be by substituting values for the variables. All right, example one, working with this formula. Now, when we worked with exponential functions, we worked with this formula, which is our compound interest formula. So let's just review how that works. A is the amount at the end of a time frame. The P is your principal amount that you're investing. So we're going to calculate the A. The principal is $1,000, and we're investing it at 5%. We'll assume that's just annually. I didn't specify, but it is annually. So we'll just sub that in for our I, and our N is 10. So there's 10 compounding periods, whatever it happens to be. So then you're just going to pop that into your calculator and get an answer for that. And that should be, I'm just doing that right now along with you, hopefully. I got the wrong answer on my calculator. Let me try that again. I think I just forgot a zero. I get $1,628, and money goes to two decimal places, so we'll put 89 cents behind there. All right, so that's just straight up substituting values into a formula. That should not be an issue at this point. That's like a grade 9 skill, grade 8, grade 9 skill. All right, part B is where we get into our little bit more interesting type of question. What type of function is A if P equals 1,000 and I equals 5%? So if we just sub those things in, we're not going to be able to evaluate because we're still going to have an unknown here. So we're going to have our 1.05 with an exponent of n. Now, because the independent variable is an exponent, that makes it an exponential function. Okay, so that's what we're meaning when it says here, you can determine the type of function a formula represents when some of the variables are replaced with values. So that's an exponential function. All right, so if I look at that formula again, but this time I'm subbing in a value for I, 1.05, and then we get our value in there for n. This part here will actually just evaluate to be a number. So let's try that, 1.05 to the exponent of 10. Oh, it gives me a great big decimal number, but really what that is it means I have a number multiplying a letter. So it's like a coefficient. I could put that value out front, which on my calculator I got 1.62889467, and I'm sure it just rounded that off, but this is just an independent variable with an exponent of 1. That makes that a linear function. Linear function. We don't normally write that exponent of 1 in there, but we could have that. So even though it's a capital letter, it doesn't really mean anything. It's just a linear relationship. You could think of this as your m. Let me not use the eraser tool on that. This really is the slope times your x, and this is your y. Y equals 1.05 to the exponent 10 times x. All right, I'm going to go to the next slide here. Rearrange or solve the formula for I. So our formula is still the same one we were working with. Excuse me. Our formula is the A equals P 1 plus I to the exponent of n. Now what we want to do here is get the letter I all by itself here. So we have to undo the things that are around it in the opposite order of bed mass. So the 1 is attached to it within brackets, so it's going to be the last thing I excuse me, undo. I have a multiply by P and I have an exponent of n. Exponent is right after brackets, multiply is further out. So my first step is I'm going to divide both sides to undo the times by P. So I'm going to divide both sides by P, and I'm going to end up with an A over P equaling 1 plus I to the exponent of n. Now, if that was an exponent of 2, I know I could undo it by square rooting. If it was an exponent of 3, I could undo it by cube rooting. But since it's an exponent of n, I'm going to undo it by nth rooting, taking the nth root of both sides. So make sure that that root symbol covers the entire a divided by p. And that leaves us with a 1 plus I. And then to get I by itself, I'm going to undo the plus 1 by subtracting 1 from both sides. So I end up with I being equal to the nth root of a divided by p, and then minus 1. And make sure that the minus 1 is not underneath the root sign. If you're rearranging and things are not clear, like you don't have the root symbol going around the entire a divided by p, it won't be marked correct. So just be sure you communicate what it is that you mean. All right, our next one is we're going to take that same formula, but this time we're going to solve for n. We want to get n by itself here. So again, I'm starting with the formula. A equals p times 1 plus I to the exponent of n. Now I want to get n by itself. The first thing I'm going to do right now is what I did first the last time. I'm going to divide both sides by p. I'm going to undo that p. And we're going to have a divided by p being equal to a 1 plus I to the exponent of n. Now this is kind of nice because it does go back and review the things that we did in our logarithmic functions unit. I can't solve for an exponent. What I'm going to do is take the common log of both sides. So I'm going to do the log of the left side, which is the a divided by p, equals the log of 1 plus I to the exponent of n. And then we can apply that log law that's going to pull that n down front, and we're going to end up with the log of capital A divided by p is equal to n times the log of 1 plus I. All right, now my last step to get log by itself, n by itself, it's being multiplied by this log. So I'm going to divide it away from the n. But if I do that to that side, I have to do it also to the other side. Got to keep it fair. All right, so my final answer then, I don't know if I can slide this in here. Our n will equal the log, it doesn't look pretty, but it's log of a over p divided by the log of 1 plus I. That's supposed to be a plus sign. Having trouble making it work. There we go. The log of 1 plus I is what that says there. All right, we have another question here on this side. Okay, an open belt pulley system is shown. It's not a super awesome diagram, but it's one I pulled out of an old book we have. A larger pulley has a diameter of 6.25 inches or 6 1/4 inches, and the smaller pulley diameter is 4 1/4 inches. The belt is 56 inches long that goes between these two wheels. Find the distance between the pulley centers using the formula, and all the variables are defined here. All right, why don't you give that a try, see how you can do with that, and then you can check your answer. Okay, we want to find the distance between the pulley centers, which is this variable x here. Okay, we're trying to solve for x. That means we should know everything else here. So our L, the belt length, that's our 56 inches. The diameter of the larger pulley is 6.25 inches, and the diameter of the smaller one is 4.25. So we're going to sub those values into the formula, which means I will have 56 being equal to 3.14, 0.5 times D, and D is 6.25, capital D that is, plus 0.5 times little d, which is the small diameter, or the diameter of the small wheel. That's a big bracket. And then we have our plus 2x. So the goal here is to get our x all by itself. All right, so I'm going to work inside the brackets. I'm going to do the multiplication in there, 0.5 times 6.25 I get a 3.125, and I'm going to add to that 0.5 times 4.25, and I got a 5.25. So I'm just going to jot that step in here, just so that you can follow along. So this entire bracket boiled down to, evaluated down to 5.25 here. Okay, so this entire thing became that piece. All right, at this point I'm going to multiply that 5.25 by 3.14, and that gives us a 16.485. And that's a 2x there. So then I would subtract that 16.485 from both sides. So I just made it negative and added it to the 56, and I got a 39.515, and that's equal to 2 x's there, and then divide both sides by 2, and I get a 19.7575. So x is equal to 19.7575. Okay, so therefore the distance between the pulley center would be, will be that length. So I'll just write a therefore statement. Okay, therefore the distance between the pulley centers is 19.7575 inches.